Recording in progress.
Right, okay, Tando, we're right back. My sincerest apologies for the power loss that led to a sudden cut in the communication. But we actually are dealing with mechanics, and we're looking at two forces of magnitude 50 and 80 newtons, okay? 50 and 80 newtons as shown below, act at a point on a Cartesian plane in the directions shown in the sketch below. So you have the directions shown. And once again, the 80 Newton force acts on the horizontal, and we can clearly see the 50 Newton force acts at an angle of 30 degrees to the horizontal. And we continue. Okay, the examiner says give the correct term for the following description: a single vector having the same effect as two or more vectors together. We actually were able to resolve that, and we're able to come to a common conclusion. And we say that must be the resultant vector. Okay, good. Right, we said that is the resultant vector. So we note that one down. So we say it is nothing other than the resultant vector. Okay, if you don't want to call it the resultant vector, we call it the what? The net vector. The net vector. But obviously the most correct description is that of a resultant vector. So we're good. Let's look at the next question, please. Right, that was part A of the set of questions, and we're looking at part B right now. Right, let's look at part B. Okay, in part B, we need to calculate the, okay, number one, magnitude of the vertical component of the 50 Newton. For 2 marks. Number 2, we want to find the magnitude of the resultant or net force. For 5 marks. In number 3, we want to be able to calculate the direction of the resultant net force. Okay, let us look at these particular problems here. To calculate the magnitude of the vertical component of the 50 Newton force. Okay, and we remember that this is the diagram. This is the sketch. And we can see the 50 Newton force, acting at an angle of 30 degrees to the horizontal, and we can see the 8 Newton force acting along the horizontal there. Okay, we are interested now in using this diagram, but also answering specific questions. This one of the vertical component of the 50 Newton force. Okay, let's look at this one step by step. So we proceed to look at the solutions to this. Right, we look at the solutions. So in looking at the solutions, we shall look at the question or the solution to the question B1. How do we find the vertical component? Okay, the couple of things you need to remember, and I know that this is very straightforward, okay? You have the force there of 50 newtons. And this force of 50 newtons acts at an angle of 30 degrees to the horizontal, and we have another force here of 80 newtons. And this one acts along the horizontal. Okay. The first question wants us to find the vertical component of the 50 Newton force. So the couple of things we need to note, but also we need to remember, okay? And I'm going to draw sort of a diagram here. The components. So at this point, what you need to look at is the horizontal component of the 50 Newton force. Can be constructed and be drawn this way, and obviously together with the vertical component of this here. So which means therefore that here you have fx, fy. So you have the horizontal component fx and the vertical component is fy. We're interested in the vertical component. So the formula for the vertical component we use at this level is that fy is f, the trigonometric sine of theta. So in other words, to find the vertical component, we take the force until we multiply by the sine of the angle there. Okay, good. So what is the meaning of all this? F sub y is actually 50 newtons times the sine of 30 degrees, which is 50. Sine of 30 degrees is exactly 1/2. Can use a calculator there. Okay, so if you use a calculator, you'll be able to realize that the sine of 30 degrees is precisely 1/2. And if you actually are able to see that the sine of 30 degrees is actually 1/2, so that is going to be precisely half of 50 is 25. Half of 50 is 25 newtons. Okay, but let's look at the question and look at the question very, very carefully. We are to calculate the magnitude of the vertical component. The minute the examiner asks you to find the magnitude, the examiner does not want any direction. They don't want any direction. What they want is only the size of the vertical component. And at this point, we have just found it. And here it is. Given the force of 50 newtons acting at an angle of 30 degrees to the horizontal, right, we are able to find the vertical component, Fy, and we use F sine theta, okay? And therefore, the sine of theta, 30 degrees in particular, is a special angle, and we can be able to get that there. Okay, now there's something we can remember. Let me use let me proceed on the next slide. Okay, for example, just something to recall about what you call the spatial angles. What are the spatial angles? So if you have this, right, if this angle is 60 degrees, this one is 30 degrees. This side is going to be the square root of 3, 1, 2. So that if you have, for instance, the sine of 30 degrees, using our usual SOHCAHTOA, right, to be able to see that the sine of 30 degrees sine is opposite of hypotenuse 30, and opposite of hypotenuse is, this is the opposite one. Hypotenuse is the longest side of the triangle, opposite the 90-degree angle, and therefore we have sine 30 is exactly 1/2. Let's look at the next question, please. The magnitude of the resultant net force. What is the magnitude of the resultant net force? Okay, let's look at this one. Okay, now at this point, we remember that we are looking at B2. Right, looking at B2, you remember that we have the diagram like so. And we have that this here is the angle of 30 degrees, 50 Newton force, 80 Newton force. We are interested now in finding the resultant vector. Magnitude of the resultant force, or net force. Okay, now to find the resultant force, or net force, there are a couple of things you need to remember, okay? We need to find also the horizontal component Fx, because if we agree together that there are forces acting on at this point, and we have together here the vertical component, the horizontal component. Okay, now how do we then find the horizontal component? Okay, Fx is actually F cosine theta. That is the formula for the horizontal component. The force applied is 50 newtons multiplied by the cosine of 30 degrees. Okay, one uses a calculator for this, and 50 newtons times cosine 30 degrees is actually 43,3. 43,3 newtons. Right, so once we have these, so we have both the vertical and the horizontal components, and therefore we want to find the resultant vector. So let us continue to analyze this question. Still looking at B part 2, we have this one here. We have that one there. And then we have this force that acts in that direction, and another one acts that way. Is our Fx, this one is our Fy, and this is our force F of 50 newtons. Right, we have 80 newtons here as a force on the horizontal. Right, so this Fx, we know very well, that is 43,3. And Fy is actually the same as 25 newtons. Okay, this one is 30 degrees. So now I want us to analyze this question and find the resultant on a force. Now, one way to do this, we need to find the resultant component for the forces in the x direction, right, or along the x-axis. So to find the resultant there, we'll have to take the force of 80 newtons. In other words, we choose this side, this direction as positive. So that we have 80 newtons minus 43,3, which is the same as 36,7 newtons. So we have 80 minus 43,3, which is 36,7 newtons. That is the resultant force along the x-axis, or in the x direction. And then now we want to therefore find the net force. what is then the net force at this point? F net. Right, so we look at the net force. Now to find the net force, we actually therefore can be in a position to analyze these and say F net. Right, F net, so in other words, F net squared is Rx squared plus Fy squared. Okay, so we're dealing with this kind of a situation here. We have 50 newtons there. But we have seen therefore that Rx okay. We've seen that Rx is this one. Okay. And then we have Fy. We found Fy to be 25 newtons. All right, and this angle here is 90 degrees. So we use Pythagoras theorem to find the actual net force there. So which means therefore that F net which is 36,7 squared plus 25 squared. Right, so if this is the case, we then are able to use a calculator and see therefore that F net is the square root of 36,7 squared plus 25 squared. And this is the same as what? 44, 41 newtons. Okay. So because this question was interested in us doing the B part 2, and the B part 2 was saying the magnitude of the resultant net force or resultant or net force. We have found the magnitude, so the direction is not important yet for the first part of the question. And we have found the result, but the examiner now in part 3 is really saying the direction of the resultant or net force now, B part 3, the direction of the resultant or net force, B3. B part 3. So at this point, we need to analyze this very, very carefully and realize a couple of things that we have. Right, so would remember, therefore, that what we have is in this direction, we have Rx, which is 36,7. And then we have this one here, which is the F net. And then we have this one here, which is Fy, and this is 90 degrees. Okay. This translates to this one here. So this one You can call it resultant in the x direction, which is 36.7 newtons. There is F net. We found it, 44.41. Resultant in the y direction, 25 newtons. And therefore now the net force here is 44.41 newtons. And so there are a couple of things that are very important. If we put this angle and call it theta and call this the angle phi. So in other words, this is the phi symbol. And this symbol here is the theta symbol. Okay, so with that said, we're in a position to find the direction of the net force. What is the direction of the net force? This one. So you can use the tangent, popular to use the tangent. So the tangent of theta becomes, in this parallelogram that we've got, so the tangent of theta is going to be 36.7 divided by 25. So the tangent of theta therefore becomes opposite theta. So because this force here is 36.7 is parallel to this, so you can imagine this being also this side, forming this side of the triangle, so that we have the opposite over adjacent. Opposite is 36.7 over adjacent, which is 25 newtons. And then we use the calculator. Using calculator, we have arctan of 36.7 divided by 25. Right, okay, look at this carefully and make sure you understand what's happening here. So this is the angle theta. In the direction the examiner wants is this one. If you use the calculator, you'll get 55.74 degrees. Okay, so this is basically the direction of the what? The direction of the net force. How did you get the direction of the net force? We actually, to find the direction of the net force, we found the direction at this point between two specific forces. What are the specific forces? They are the 36.7 newtons. Okay, parallel to the side of the triangle, meaning we can always move according to the parallelogram law. We can always move forces as long as we do not change the direction of the forces, but we can change the position of the forces. So you can change the position of this and put it there. Okay, if we put it there, then we have 36.7 newtons, and this one is 25 newtons. And therefore, if you look at the resultant vector in the x direction, the resultant vector in the y direction, and then we're able to get the direction of the resultant force, which is actually this net force there. So we found the angle theta. Okay, we found most certainly the angle theta there. So, right, so look at that and think about these and make sure that you understand what is happening here. Understand what is happening there. Okay, we continue and we analyze these in detail. The next question. Right, the next question is as follows. Right, stay tuned to see the next question as we look at these. Okay, let's look at this question. Here's the next question. Right, this question says that there is a box. A box with a mass. Right, with a mass of 45 kilograms. Right, this box is pulled with a force of 90 newtons. With a force of 90 newtons at an angle of 50 degrees to the horizontal. Right. Okay. Furthermore, the box moves at a constant velocity, at a constant velocity. And then now we have the situation. If we draw like this, here is the box, and there's a mass of 45 kilograms. So 50 degrees. Ninety newtons. Okay, we have that kind of a situation there. Okay, I want us to analyze this, but very, very carefully. Right, if this is the sort of situation that we have, here is the first question. Number one, define the term kinetic frictional friction force. Okay, what is the answer to this question? Anyone? Anyone? Okay, the examiner is asking us to say, define the term kinetic friction force. Who knows what kinetic friction force is? Who knows? Anyone?
So I think it is a force opposing the motion of an object.
Okay. Right, you are on point. But this is how we state it. The force. The force that opposes the motion. The force that opposes the motion of a moving object. Okay, you see, you are right, but you were half right. Relative. relative to a surface. You see, you are half right because you said it is the force that opposes the motion of an object. So it is the force that opposes the motion of a moving object. It does not only oppose motion, but it opposes motion of a moving object, because there is not only that we have kinetic frictional force, but we also have what we call the static frictional force. So it's very important that you have the keywords like the force that opposes the motion of a moving object relative to a surface. That is called the kinetic friction force. Next question. Number 2. Number 2. Okay, we must learn some of these things we're going to use here to do the calculations. Like students must be able to state Newton's first law. Law of motion. In words. Normally that one is given 2 marks in the exam. Normally it is given 2 marks in the exam. So let us see who can do this one. You forget the laws sometimes. I could already imagine. Does anyone know Newton's first law of motion in words? What does this law state? What does it say in words? Here is the statement that we accept in this in answering these questions in physics. We say a body will remain in its state of rest or motion at constant velocity. At constant velocity. Unless a non-zero resultant or net force acts on it. So a body will remain in its state of rest or motion at constant velocity unless a non-zero resultant or net force acts on it, and this is called Newton's first law of motion in words. Newton's first law of motion in words. So you note this law and make sure that you understand this particular law. What does Newton's first law of motion say in words? This one you need to know for both metric and grade 11. Grade 11 and metric, you need to remember this law because it's examined at both levels. So make sure you learn it and you understand it. That the law states that a body will remain in its state of rest or motion at constant velocity unless a non-zero resultant or net force acts on it. The next point. Next question. Okay, let's look at what we need to do now. Part 3 of the questions. Number 3. Right, number 3 is easy. Let's do a calculation. So let us calculate. Let us calculate the magnitude of the horizontal component. Of the horizontal component. Of the applied force. Of the applied force. Okay, this one would be given like 2 marks in the exam. But let us analyze what is happening here. So we have the surface. And we have a block like this of a gross mass of 45 kilograms. This force of 90 newtons acts at an angle of 50 degrees to the horizontal. Okay, if this is the sketch, the examiner is asking us to calculate the magnitude of the horizontal component of the applied force. And we can see that the applied force is actually the force of 90 newtons. So now let us look at this, but look at this very carefully. So the marks here are like 2 marks. And this is the diagram. So let us look at the solution in yellow. Right, looking at part 3. Want to calculate the magnitude of the horizontal component. We have learned that the horizontal component has its formula as F subscript X, which is F cosine theta. This is the formula for the horizontal component of a force. And therefore, because the x-axis itself is horizontal, that is why you have F sub X, which is now the force itself here applied is 90 newtons. Cosine 50 degrees. Ninety cosine 50, which is actually 57,85 newtons. 57,85 newtons. So this tells us that we have found here the magnitude of the horizontal component of the applied force. This is the applied force of 90 newtons, and its horizontal component is the Fx. In other words, if the forces act like this, you'd have a component there, you'd have another component there, and this component is the F subscript X, and this one is F sub Y, etc. And obviously the angle there is the angle of 90 degrees over there. Okay, so we have been able to answer that question and find the magnitude of the horizontal component, which is the F subscript X. And the formula for the horizontal component of forces all the time is F cosine theta. For the vertical component, it's always F sine theta. Okay, next question. Let's do another calculation. Number 4. Calculate the magnitude calculate the magnitude of the normal force The magnitude of the normal force for Fermax. Calculate the magnitude of the normal force. Right. Here is the situation, the ground. A box of 45 kilograms. An applied force of 90 newtons. Acting at an angle here of 50 degrees. And then now this one here. So, okay, this one is a force Fermax there. Okay. I know this one is very easy. Tando, what do you think is the formula for the normal force? What do you think is the normal force in this question, Tando? Too easy, Tando. Okay. Right at this point, then, to find the normal force, we realize that the normal force is the gravitational force minus F sub y, which means the normal force, gravity is mg, Fy is F sine theta. The mass is 45. 9.8 minus 90 times the sine of 50 degrees. Okay, you realize that here you'd have the F sub x, F sub y. And this box here has its own weight, which is through the center of gravity. So when that happens, then you'll be able to have the right, you'll be able to see that now for us to find the magnitude of the normal force, you have to look at the vertical forces that act on this object here. If you look at the forces acting on the object, so you'd have the Fy, the vertical component, which is an upward force, and the weight is downwards. And therefore, the magnitude of the normal force at this point would be calculated as a consequence as follows. And then now you then say an interaction of the two forces, because the normal force itself is a consequence of the interaction between the ground and the object itself. And looking at this, you'll be able to see, therefore, that the force of gravity is mg, and the upward force itself is Fy, the vertical component. And therefore, if you use a calculator, you'll be able to see that this is exactly 372.06 newtons. 372.06 newtons. So Ideal, therefore, the normal force would actually be exactly that one there. Will exactly be that one there. Okay, so just note exactly how would find the normal force in this particular situation. Okay, note that. Next question. But obviously, this is the magnitude, please. So it is actually obviously without the direction. Number 5. Next question. This one is number 5 question. Calculate the coefficient of kinetic friction. Calculate the coefficient of kinetic friction. 4 marks. Calculate the coefficient of kinetic friction for a good 4 marks. Let's see how we can do this one. Just bringing the marks closer to the end of the question. Right, we need the coefficient of kinetic friction here. How do we do this? Right, okay, let's think about this. Let us think about this. You remember the horizontal, the ground, 45 kilograms, 90 newtons. Okay, now we want to find the coefficient of kinetic friction. And the formula for that one is as follows. Okay, you can use a simple F just to avoid confusion, because some of you will begin thinking this is only the F that can work. So, okay. Right, so I'm going to use F subscript K, which is mu K times the normal force. So that the frictional force in this question, because you'd remember that we have this force here and that one, Fy, Fx. Okay, 57,0,85 newtons. Okay, and then you have Fy. There also Fx is that one, we found it before in the question, one of the questions above. And then Fy is 90 sine 50 degrees. Okay, now with this said, so the Fk, okay, if you look at this question carefully, let's look at the question carefully and look at what the examiner was saying here. A box with a mass of this is pulled with a force of this at an angle of this to the horizontal. The box moves at constant velocity. Okay, so since the box moves at constant velocity, it means therefore that the forces acting on these are in equilibrium. Equilibrium. So if the forces are in equilibrium, it means a couple of things. But it means therefore that the frictional force, the force of kinetic friction, and the Fx are equal. So in other words, Fx is minus Fk. Okay, they're equal magnitude but opposite in direction. So, which means for Fk now, you're gonna have 57,85. Okay, it's gonna be equal to the F-axis is equal to Fk because the box is moving at constant velocity. So the forces acting on these are actually in equilibrium. And therefore this equals mu subscript K. The normal force is the one we got. We got the normal force to be 372,06 newtons. That's what you put here. 372,06. Okay, newtons. Okay, we use N for the normal force, capital N. Okay, we can use other symbols as well. But as a consequence, this means mu subscript K is 57,85 divided by 372,06. 0,16. Okay. It therefore means that the coefficient of kinetic friction is 0,16. 0,16. Number 6. Will, it's another question, this one. Will the coefficient with the coefficient of kinetic friction change if the angle of the applied force is decreased. Right? Right only yes or no, and give a reason. So, and the marks are 2. Will the coefficient of kinetic friction change if the angle of the applied force is decreased? Okay, so in other words, you'd remember that at this point, what we have is you have this is the ground, and this is 45 kilograms, 90 newtons. Okay, if that is 90 newtons and this is 50 degrees. Okay. Then if the angle of the applied force is decreased, so it's 50 degrees now, what about if somebody makes it smaller? You make it 20 degrees, you make it 5 degrees. Will the coefficient of kinetic friction change? Let's look at this question. Well, the simple answer to that is if we just reduce the angle here, no, it's not going to change. The coefficient. Right, so, okay, just write clearly here. The coefficient. The coefficient is dependent. It's dependent on the nature right, on the nature of surfaces. Or type of material. Or type of material. In contact. Okay, if we reduce this, we argue that the coefficient of kinetic friction is not going to change because it's the coefficient of kinetic friction, or the coefficient is dependent on the nature of surfaces or the type of material in contact. So it's not going to change because an angle is being reduced there. So just something to note there as a matter of fact. Next question. Next question. Okay, next question. The gravitational the gravitational force on a probe called curiosity on the surface of Mars is a 3,308 newtons. The radius of Mars is a 3,390 kilometers. And the mass of the planet is a 6,39 times 10 to the 23 kilograms. Okay, we start by saying the gravitational force on a probe called Curiosity on the surface of Mars is this 3,338 newtons. But the radius of Mars is 3,390 kilometers, and the mass of the planet is 6,39 times 10 to the 23 kilograms. First question. State Newton's law of universal gravitation. In words. Okay, let's look at this. State Newton's law of universal gravitation in words. Okay, let's see what we can do here. What is the statement of Newton's law of universal gravitation in words? Here is the principle, and it says that each particle in the universe attracts every other particle with a force, with a gravitational force. With a gravitational force that is directly proportional to the product Okay, this T is too close. Right, directly proportional to the product. Directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Okay. Between their centers. Okay. All right. So, okay, this is distance. This is distance. Not just distant, but distance. So each particle in the universe attracts every other particle with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Next question. Here is the next question. Calculate the mass of the probe. Calculate the mass of the probe. Okay. Look at the solution to this. So Gm1 m2 over r squared. The force of attraction here is 338. G is the universal constant, 6,67 times 10 to the minus 11. Okay, so G is a constant and it is always 6,67. Want to find the mass of the probe? If you know that the mass of one of the planets the gravitational force on a probe called Curiosity on the surface of Mars is this. So the gravitational force is this. The radius of Mars is 3390 kilometers. And the mass of the planet is this one. So you're going to use the mass of the planet. The mass of the planet is 6,39 times 10 to the 23. And therefore, this is divided by the radius of Mars, which is 3390. Okay, and we calculate here and we use the calculator. We make M the subject. If you make M the subject, you cross multiply this to this and you divide on a calculator and you'll see that the mass of the probe is 900 kilograms. So the mass of the probe is actually 900 kilograms. The mass of the probe is 900. So we use this formula for Newton's law of universal gravitation. The force of attraction between any two objects of masses m1, m2 is directly proportional to the product of the masses and inversely proportional to the square of the distance between the centers of the objects. So this is the law of universal gravitation, Newton's law of universal gravitation. Let's look at the next question. Okay, so the next question. Number 3, calculate the weight of the probe on Earth. Calculate the weight of the probe on Earth. Calculate the weight of the probe on Earth. So let us do this one of the weight of the probe on Earth. Okay, now to find the weight of the probe on Earth, the weight is mass times gravitational acceleration. W is equal to mg. The mass, we already have seen that according to this question here, calculate the mass of the probe. So the mass of the probe is 900 kilograms. The mass of the probe is 900 kilograms. So we're going to use that into 9.8. 8,820 newtons. $8,820 So just note that part. Just note that part. Calculate the weight of the probe. So the weight formula is mg, and therefore we got the mass of the probe 900 kilograms, and the gravitational acceleration on Earth is, okay, the gravitational acceleration is not always 9.8 on other planets, but we are saying on Earth. So on Earth it is 9.8, and you get exactly this if you use a calculator. Let's look at more questions. Let's look at more questions. Right, let's look at more questions like so. Okay, we're looking at the next question. Right, I want to bring other questions that are very interesting and much nicer. See, much nicer questions like this one's here. Right, here's one question, very straightforward. See, let me use a white color. In which of the following pairs do both items refer to vector quantities A, mass and weight, B, acceleration and weight, force and mass, D, time and acceleration. In which of the following pairs do both items refer to vector quantities? We know that at this point, if you look at this very carefully, we are looking at both vector quantities. So now if we were to look at both vector quantities, right, here mass is a scalar and the weight is a vector. Acceleration is a vector and weight is a vector. Force is a vector quantity and mass is a scalar, time is a scalar, and this is a vector. So if I look at both vectors, then we are convinced that the correct option is B. Correct option is B, so we're looking at both acceleration and weight. Okay, next question. Next. Okay, let's look at the positively charged object. A positively charged object has A, more electrons than neutrons. B, more protons than neutrons. Equal amount of electrons and protons. D, more protons. More protons than electrons. Okay, so we have this. Let's look at this and decide on the answer. A positively charged object has what? More electrons than neutrons, more protons than neutrons, equal amount of electrons and protons, more protons than electrons. Okay, so let's think about this. So, okay. We're looking at a positively charged object. So a positively charged object basically would have more protons than electrons. So the correct answer would have to be this one. This is like MCQ. Right. MCQ is multiple choice question. Multiple choice question. So a positively charged object has more protons than electrons. It has more protons. That's why it's positive. More protons than electrons. Okay, next question. Which of the following graphs best represents the relationship between the potential difference V across an ohmic conductor and the current I in the conductor. At constant temperature. Okay. Right. So let's answer this question. B VI C. VI D. Horizontal VI. Okay, let's look at this one. Right. Right. So, okay. So which of the following graphs best represents the relationship between the potential difference across an ohmic conductor and the current? V, according to Ohm's law, because we're looking at an ohmic conductor here, V directly proportional to I. So this is the correct one. Okay. Okay, so just look at that one. Because V is directly proportional to I, so it means that V and I are directly proportional, and therefore you'll have this linear relationship like that. Okay, this is as a consequence of what you call Ohm's law. Now, the other things that I want us to discuss here, the other things I want us to essentially discuss. See what else we can discuss. There are too many things we can look at. Right, so here, if you say, right, in which vector diagram below is the following statement true? Okay, and the statement is vector A is vector B together with vector C. So you have this one. Okay, yeah, so Okay, so you have this. B. Okay, this is exactly what we have. And then there's another vector diagram B. You have a force that acts like that, or a vector in that direction. There's another vector in this direction. And there's another vector in that direction. Um, DAB, and then there's D. There's a vector like this. And then there's a vector that way. And then there's a vector like so. C, A, B. Okay. In which vector diagram below is the following statement true? So we're saying vector A equals the vector sum of B and C. So now we're asking the question, which one is the correct one? Which one is the correct one here? So look at this very carefully and reason. In which vector diagram below is the following statement true? Vector A is vector B plus vector C. So if you look at these, what do we have? So see that vector B plus vector C gives us vector A. So the very correct one would have to be part C. So vector B plus vector C is going to give us vector A. Vector B plus vector C is vector A. So the correct one is C, and the others are wrong. Because here, for instance, you can see that this one will be vector A, and then vector B and vector C, etc. So you would actually realize, therefore, that the correct option would be exactly part C. Because if somebody travels from A in the direction of vector B and then direction of vector C, it will be the same as just taking one trip from here to there in the direction of vector A. All right, so, and obviously there are a lot of ways you can use to sort of reason this out. Okay, if you look at this one, for example, you can move vectors, but never change the directions. So if you move this one and you make it parallel to this, you'd realize therefore that you'd move here, you'd move there, you'd move there. So you'd move, it would say, for instance, C and A would give B. C, then A would give B. So it's not exactly what this one says, And if you move this one here, for example, you realize that it would actually not be exactly as this says. And as a consequence, we are convinced that as a matter of fact, this vector diagram here in C is exactly what the question precisely wants. Okay, so I want to emphasize a couple of things here, that this one is in that direction. This one is down, this one is that, so we have something exactly like that one there. Like that one there. Okay, so, and this one here, just look at the directions carefully. It's the arrow up, down, and this one further to right, and this one here is to the left, and this is down, and this is down, and this is in that direction, and this is towards, is sort of downwards, and this one is the vector base upwards. So, and obviously in view of these particular options here, we're able to see that the correct answer would be better description. The best description would therefore be the vector diagram C. The vector diagram shown in C. Okay, so you think of this and make sure you sort of can make sense of these particular questions. Let's look at an astronaut. Let's look at an astronaut. Right, an astronaut has a weight Fg on Earth. What distance in terms of the radius of the Earth R will the astronaut okay will the astronaut be if his weight, okay, we just lost power,